So hello students. So this will be a course on lecture. So this will be a lecture on the four vectors that arises in the context of special relativity or in the context of general relativity. Knowing four vectors would eventually help you to solve some of the most important problems that we often encounter in the domain of theoretical physics. So before discussing about four vectors, we'll be first discussing something called as the three vectors, right? So, what is a three vector? Three vector is basically the vector that you define in the usual Euclidean space. So, you can say that the vector defined in the usual Euclidean space. Usual Euclidean space. That is, if I say that capital A is some kind of a physical quantity, and that is a three vector. So we can rewrite this vector, or we can express this vector as a sum of the components such as the x component of A, the y component of A, and the so-called the z component of A, right? And you must also know that in order to call any physical quantity a vector, it must obey some certain rules. So the rules are that it must obey vector addition, provided that there is a physical quantity and that physical quantity obeys the vector addition theorem or vector addition, we can call that as a vector. In a similar context, we'll be now talking about something called as the four vector. Now what is a four vector? So a four vector is a quantity, or you can say that it is a vector which is defined in a four-dimensional space-time continuum. Now the only difference that you can notice over here, that a four vector is a vector which is defined in a four-dimensional space-time continuum. Now students, you must notice something, that I haven't written space-time as space-time because when we talk about relativity, space and time are considered as one. Time is also considered as the fourth component of the dimension, fourth component. So in relativity, you must always write space-time as like this. So basically, four vector is a vector that is defined in a four-dimensional space-time continuum, or you can say, or in Minkowski space-time, or in the Minkowski space-time. So even in Minkowski space-time, now let me give you a brief idea about the Minkowski space-time. When we talk about the Minkowski space-time, we take this, suppose I am taking that this is the x direction or the x component, and the time component is usually taken as ct. Now please note this thing, that in case of relativity or in case of Minkowski space-time, the time is taken to be ct and I am taking only the x component. That means that I am assuming that the motion is occurring along the x direction, and this is the time, that is ct. Now you might wonder that if t is the time, then why am I multiplying that time with some parameter c? What is c? Now students, c is nothing but the speed of light, that is 3 into 10 to the power 8 meters per second. Now why are we multiplying c with t if t can be represented alone? You see students, c has the unit of meters per second and time has a unit of second. So if you multiply c and t, the dimension of ct becomes that of the meter. So the factor c is multiplied with time so that we can make the dimension of ct same as that of the x. And it is very important to note that whenever we talk about Minkowski space-time, time is always represented by ct. You can remember this particular fact. Okay. Now moving on to the next topic, that as we were talking about four vectors, right? And as I've just told that a vector which is defined in a four-dimensional space-time, that is called a four vector. And as I've just told you, that even a three vector or a vector which is defined in a usual Minkowski spacetime, in order to call that quantity a vector, that is in the Euclidean space, it must obey some certain rules. That is, it must follow vector addition. In a similar manner, I cannot randomly call any physical quantity a 4 vector. To call a certain physical quantity a 4 vector, it must obey some certain rules. As I am saying, any physical quantity for any physical quantity to be a 4 vector, it must obey some certain rules. And what are the rules? The first rule is that it must obey a transformation equation. It must obey a transformation equation. Now, what will be the transformation equation? I will derive it in a couple of minutes. So the second point is that the 4 vector, or you can say that the magnitude of a 4 vector must remain invariant under Lorentz transformation equation. Now, this is the second point, that the magnitude of a 4 vector must remain invariant under the Lorentz transformation, or you can also call it that, or you can also derive this as the inner product of a 4 vector is always Lorentz invariant. Now, I know that this statement might seem a bit high level, but I will be explaining them in a couple of minutes. So you can take down these points as when can you say that a particular physical quantity can be addressed as a 4 vector? It must obey a transformation equation, and the inner product or the magnitude of the 4 vector is Lorentz invariant, right? So now moving on to what do I mean by the first statement when I say that it must obey a certain transformation rule. So before moving to the first point, let me first write down few important things that I would require in order to write down the transformation equation. So let me first write down the so-called, the very famous Lorentz transformation equation. The Lorentz transformation equation. So first of all, let me write it as T bar will be gamma multiplied by T minus V upon C square into X. This is the equation for time. Then we have X bar equal to gamma X minus Vt. Then we have Y bar equal to Y and Z bar equal to Z. Now what are the meaning of it? So you see students, gamma is nothing but the Lorentz factor, which is nothing but 1 upon under root 1 minus beta square, where beta is nothing but V upon C, right? So what is the Lorentz transformation equation? So these are the transformation rules that connects two different inertial frames S and S prime, or you can say S bar, in a such a manner that one of the frame remains at rest and the other frame is moving with a constant velocity v along the positive direction of the x-axis. This is what I have assumed. As you can see, I have written x bar or x bar equal to gamma times x minus vt. So, and t, I mean you can see from the equation that x is changing, time is changing, however y and z remains the same. That means I have assumed that the frame is progressing along the positive direction of the x-axis. The time is changing according to the relativity, because relativity says that for two different observers the time will be different. Now that is in the different context when we are coming to time dilation. But these are the frames, or these are the equations that connects two different inertial frames of references S and S bar, right? So, and now I'll be introducing one more thing, that is the convention And what are the conventions? So the conventions are x naught as x, x1 y, x2 as x naught as ct, x naught as x, x2 as y, and x3 as z. Now what are this? Now you see students, in place of writing again and again x, y, z and time, I will be replacing them with x1, x2, x3 in the case of x, y, z, and in case of time I will be representing it with x naught. Now you might wonder, why haven't I written CT over here but I have introduced CT over here? Now I'll be rewriting all of them in terms of CT or in terms of these conventions. Kindly follow this. So you see students, these are the conventions that is usually used in case of S frame, while in case of the S bar frame I will be representing them as x naught bar, x bar 1, x bar 2 and x bar 3. Now x bar naught or x 0 bar, this is basically CT bar. X bar 1 is your x bar or the x component or the x axis. X bar 2 is the y bar and x bar 3 it is the z bar. Now these are the conventions that I will follow for the S bar frame or the S prime frame, whatever you want to call it. So these are the couple of conventions that I will be following. Now moving back to this. Now as I've just told that in case of relativity or in case of the Minkowski's geometry, we will be representing time as CT. So what I'll do is I'll multiply C both sides in the first equation and I'll get CT bar will be gamma, this will be CT minus V upon C into S. I believe you can follow this if you multiply C both sides. So you have CT over here and minus C into V divided by C square. So you'll have this. Again in this you multiply. So and what have you done is you have basically replaced the time with CT, and in order to do that you cannot just simply put C in the equations. In order to do that you have to multiply because T lies on both sides of the equations. Now in this context what I'll do, now I'll have to introduce C over here because as I've just told that the time will be represented by CT. So what I'll do in this context, I'll write it as x bar equal to gamma, where gamma is of course this parameter, x minus, now remember students, as I've just said, I'll replace T with CT. So for that I'll be using a very simple trick. I'll divide with C and I'll multiply with C, and this is what I get. Have you followed what I've done? I've divided with C and I've multiplied with C. So now this is the time component and this is what it becomes. In case of Y bar it remains the same. In case of Z bar it remains the same, right? So as you have seen, now these are the equations that I would require now. Now using these equations or I'll try to express these equations in terms of this equation. So what I'll do, I'll try to express this using the conventions. So as you can see students, CT bar will be represented by, so I'll call this as equation 1, and 1 can be written as CT bar becomes x naught bar, which is equal to gamma, this becomes x naught minus V upon C into, this can be written as x1. Do you follow this? Okay. Now this will become x bar, this will become x bar 1 because this is the x bar coordinate or the x prime. Gamma times x1 minus V upon C, this will be x naught. Do you follow? Right. After this I'll rewrite this as y bar, this becomes x bar 2 equal to x2 and this will be x bar 3 will be x3. Now these are one set of equations and these are the other set of equations, and I will be using them to write down the transformation equation that I have just told. So you can take screenshot or you can write down the equations. Okay, so students, so these are the equations of the Lorentz transformation equation. The first one using the convention that I have taken Ct as the temporal coordinate, and x bar and y bar and z bar are the readings in the, or the values in the s bar frame, and Ct, x, y and z are the values or the readings in the s frame. Now these are the same equations but using the conventions. Now I believe what I have done in the previous section, I believe when I multiplied with c, I did not cancel out this c square. So when you multiply with c, eventually you are also doing c times v upon c square. So one c in the numerator and one c in the denominator gets cancelled out, leaving only v upon c. So kindly check that fact. So right, okay. So now we'll try to express this equation, I mean to say this equation in the matrix notation. Please follow this, what I will be doing. So this can be written as Ct bar, x bar, y bar, z bar, which is equal to some transformation matrix that relates this set of variables with this set of variables Ct, x, y and z. So let me first write down what will be the transformation equation. You see, I am basically relating the Ct bar and the Ct, right? So the coefficient of, so let me write down, it will be gamma minus gamma v upon c 0 0. The second line will be minus gamma v upon c gamma 0 0. The next line will be 0 0 1 0 and the other one will be 0 0 0 1. Now let me explain what I have done. So when you take the first line, you can see that the coefficient of Ct is gamma, because you are expressing this equation or this side in terms of this side. So the coefficient of Ct is gamma, and the coefficient of x, that is minus gamma times v upon c, and then you are writing in between x bar and x. So you must remember, students, that the first term will be assigned only to the temporal coordinate. So as I have done over here, when you are writing Ct bar and Ct, the coefficient of Ct is gamma, while the coefficient of x is minus gamma v upon c, as there is no y and z component, so therefore 0 0. So for the next line, you have the coefficient of Ct, which is time, that is minus gamma v upon c, and the coefficient of x is gamma, there is no y and z coordinate, so 0 and 0. Now we are moving on to the next two. In case of y bar and y, there is no time component and there is no x component, so this two becomes 0. But there is y component, and then the coefficient of y is 1 and there is no z component or z coefficient, so it is 0. Similarly for the z bar and z, the coefficient of x and the temporal coordinate Ct is 0 0, and so is the coefficient of the y component. So you have only, so the coefficient of z remains 1. Now I can rewrite this in also the other form using this notation. So this will eventually become x bar or x0 bar, x bar 1, x bar 2 and x bar 3. So these are x bar 0, x bar 1, x bar 2, x bar 3, which is equal to gamma minus gamma v upon c. Now in some books, what they do is they replace this v upon c with a factor of beta, right? So you can also write beta in place of v upon c. So this will be 0 0 minus gamma v upon c gamma 0 0. This will be 0 0 1 0 and this will be 0 0 0 and 1, right? And the other matrix will be x0, x1, x2 and x3. Am I clear? Right. So students, now these are the same equations, these are the same matrices, they are no different. Just the only difference is that this is usually, this is the Lorentz transformation. This is also the Lorentz transformation, but using the sign convention, using the conventions. Now you see this matrix, as you can see over here, that is gamma minus gamma v upon c 0 0, and then minus gamma v upon c gamma 0 0, and then 0 0 1 0 and 0 0 0 1. Now this is called the Lorentz boost. Now this is called the Lorentz boost or it is also referred as the transformation matrix or the transformation matrix. Okay, so you can also write this as capital lambda mu nu. Okay, so now I'll try to now instead of writing such big equations or such big form, I'll try to express this in a very short notation, and the notations are, I mean this notation that I'm writing, this can be used for both the cases, as you will see right now. X bar mu, which is equal to sum over lambda mu nu x nu, where nu goes from 0 to 3. Okay, so as if you people remember, the first thing that I have written, that a 4 vector must obey some transformation equation. Now this is that transformation equation that I was talking about. Okay, now let me explain how it works. Suppose by the way, the value of mu goes from 0, 1, 2 and 3. I mean these are the only values that mu will take, and mu goes from 0 to 3, right? Okay, so let me try to express it. So suppose I have taken mu equal to 0, so this will be x0, this is summation, mu equal to 0 to 3, lambda 0, this is mu, this is x mu. Now as you can see, mu goes from 0 to 3, so I believe you can take a screenshot of this and then we'll move on to the next section. Okay, fine. So now we'll write down the transformation matrix for it. So now what I do is, so the transformation matrix that I had, so the transformation equation that I had was x bar mu is sum over mu 0 to 3 lambda mu nu x nu. Now where lambda mu nu is the Lorentz boost, this is the Lorentz boost, or this is the Lorentz boost, same thing. So and mu goes from 0, 1, 2 and 3. So if I take the 0th component, what should I get? Mu x0 summation nu 0 to 3, this is lambda 0 nu x nu. Now as you can see, mu goes from 0 to 3. I'll write this as lambda 0 0 x0 plus, as this is summation. The next term will be, this is 0 1 x nu x1 plus 0 2 x2 and 0 3 x3, right? Now as you can see students, x naught bar is nothing but the CT bar, which is equal to lambda 0 0, that is the first element of this matrix, which is gamma. x0 is also, x0 is nothing but your CT. If you recall the conventions, x0 was CT plus lambda 01 is the second element from the matrix, which is minus gamma, so plus minus minus gamma V upon C. x1 is nothing but x, lambda 02 is 0, lambda 03 0, so this is what you get. From this I can write CT bar is, gamma is taken as common, you have CT minus V upon C into x. So you get this equation, right? So I believe you have already seen this equation. This is the temporal equation. In a similar manner, you can also take mu as 1 and then you'll arrive at the space component for the x direction and so on and so forth, right? Okay, so now you must remember that this is the transformation rule that I was talking about, and then in the next section we will be talking about the so-called the inner product, right? Or the second point, that the magnitude remains constant under the Lorentz transformation equation. So we will be discussing about it. Fine. Okay. So in order to talk about the magnitude, what will I do? Please pay attention. So suppose I have a 3 vector, that is a vector defined in the normal Euclidean space. So if I have a 3 vector, that is Ax I cap, Ay j cap and Az k cap, right? If I take dot product or inner product, which is basically the same thing in case of Euclidean space, if I take the dot product of A with itself, that will eventually give you the magnitude of that particular vector square, right? I mean, it will basically give you Ax square plus Ay square plus Az square. That is basically the magnitude of A square, right? So now you see that this A square is a constant value. I mean, A will have a certain, I mean, if A is a vector, so the magnitude of a given vector is constant. So if I use this idea and try to understand what the inner product of a 4 vector means, so what will I do? So let's suppose, let me start with this thing, that for a 4 vector, its inner product can be written as in a similar manner that I will be doing right now. Can be written as, basically what I will be doing is, let's suppose say, okay, so let me first write it down. This is A0 square plus A1 square plus A2 square, and this will be A3 square. Now you might wonder, why have I introduced this negative sign first, and why are there 4 components? Because you see, students, when we talk about the normal vector which is defined in the Euclidean space, we usually have 3 components, x, y and z. But now I am talking about a 4 vector that also has a temporal component associated with it. So this is that A0. So I mean, suppose if I say that A is a 4 vector, and I am trying to write down its inner product. So its inner product is usually written as this form. Now why do we have the negative sign over here? It is because of the choice of the metric that I have used. Now I believe you had a course on tensors now, and I believe you know what a metric tensor means. Now metric is usually, you can say that it is a distance between 2 points which is defined in a curvilinear space-time or in curvilinear coordinates, right? And a metric tensor is usually written as G mu nu or G mu nu, depending upon what you want to do with it. Okay, so you see, students, the metric has 2 conventions. You can follow either one of them, right? So the conventions are, you can either take minus, plus, plus, plus. You can either go for this, or you can go for plus, minus, minus, minus. Now in this convention, the first minus basically belongs to the temporal component, and the rest 3 positive, it belongs to the spatial component. In the second convention, the positive sign, it belongs to the temporal component, and the 3 negative, it belongs to the spatial component. You cannot use both the conventions at the same time. You have to use either this or that, and I would recommend you, whenever you are solving any problem based on relativity, so I would recommend you that you should write down in your copy what convention or what notation or what convention of the metric you are following. It is either this or that, right? I mean, there will be no difference on what, so there will be no difference in the solution or in the answer, whether you are using this or that, the answer will be exactly the same. There might be some difference based upon the negative or the positive, but both the conventions can be used, and both of the conventions will give you the exact same answer. So I have just said that this is basically the self dot product of 2 vectors defined in the Euclidean space, and that is giving you some constant value. In a similar manner, if capital A or if this small a is a 4 vector, I have taken its inner product, which can be thought of as a dot product, and that will also give you something that looks like this. Okay, where this negative sign is usually, or this A naught usually belongs to the temporal component, and the rest three A1, A2, A3 belongs to the spatial component. Am I clear? Okay. Now, how can I express this long equation in a very short notation? Now, there is a way to do that. Now, let's follow this. Now, there is also another way to express this long equation in some other format. Now, let me write it down for you guys. So, the equation or the form is A naught, A1, A2, A3. Now, this is a vector that is written in a matrix notation multiplied by, so I have written down this because I will be using this notation, multiplied by the so-called the transformation matrix, or and this matrix basically minus 1 0 0 0 0 1 0 0 0 0 1 0 and 0 0 0 1. So this is the matrix, or that I have written down. And this is multiplied with something A naught, A1, A2, A3. If you multiply this vector or this matrix with this, and then with this, you'll eventually get this one. So how will I, because what I've done is I have usually written this form into this form. Now I'll even write it down in a much more simpler manner. Now this can be written as, A mu. Now this is nothing but the metric tensor. So this metric tensor is written, I am representing this metric tensor as eta mu nu, and this will be A mu. Am I clear what I have done? So basically I have expressed this as A mu. This is the metric tensor eta mu nu, and this as A mu. Right? Okay, fine. So let me tell you that this eta mu nu, it is the metric tensor. Right? Okay, fine. So now I'll be using some mathematics, that is the ideas or from the tensor analysis. So in order to go there, I need you people to know about something called the raising and the lowering of indices in tensors. Okay, so suppose, let me tell you something. Suppose I have a tensor that is written in this format A mu. Now you people know that this is basically a contravariant tensor or a contravariant vector of rank 1. Now what I need to do is I need to write this in this form. मतलब मेरा बात को जरा समझो, what I'm trying to say, बात को जरा समझो. तो मैंने आप लोगों को एक बात सिंपल सा बोला कि मेरे पास एक कोवेरिएंट टेंसर एक है, मुझे कोवेरिएंट टेंसर को कॉन्ट्रावेरिएंट टेंसर में कन्वर्ट करना है, या आप लोग ऐसा बोलो कि आई नीड टू कन्वर्ट अ कॉन्ट्रावेरिएंट टेंसर टू कोवेरिएंट और अ कोवेरिएंट टू कॉन्ट्रावेरिएंट. बात समझ में आ रहा है मैं क्या बोल रहा हूँ? यहाँ पे आपको कोवेरिएंट टेंसर को कॉन्ट्रावेरिएंट में कन्वर्ट करना है, या तो आपको कॉन्ट्रावेरिएंट को कोवेरिएंट में कन्वर्ट करना है. तो आप क्या कर सकते हो? बेसिकली एक सिंपल काम जो आप कर सकते हो यहाँ पे वो ये है, व्हाट यू कैन डू इज, सपोज ये आपके पास, सो यू हैव दिस समथिंग कॉल्ड योर कॉन्ट्रावेरिएंट वेक्टर. इसके साथ आप एक मेट्रिक टेंसर को मल्टीप्लाई करो, ठीक है ना? मेट्रिक टेंसर को सपोज मैंने ऐसा लिखा जी म्यू न्यू, जैसा मैंने तो बताया था. इफ यू मल्टीप्लाई a contravariant vector with a metric tensor of this sort, it will be, so the common indices are moved using the Einstein's dummy index notation, and this will become, and this, or wait a minute, I can write, and this becomes like this. Okay, sorry. So let me rephrase what I've done. So I have a covariant tensor, and I need to make up, and I need to convert this covariant tensor into a contravariant tensor. So there is a very simple rule to it. अगर आप लोगों को कोवेरिएंट को कॉन्ट्रावेरिएंट में कन्वर्ट करना, सिंपल क्या करो, एक मेट्रिक टेंसर, पर मेट्रिक टेंसर भी दो टाइप का हो सकता है, आपको ये याद रखना होगा. या तो मेट्रिक टेंसर, पहला तो इट इज अ टेंसर ऑफ रैंक 2, है ना, इट्स अ मिक्स टेंसर ऑफ रैंक 2। मेट्रिक टेंसर आप ऐसा भी ले सकते हो, मेट्रिक टेंसर आप ऐसा भी ले सकते हो, मतलब आप या तो एक कोवेरिएंट मेट्रिक टेंसर ले सकते हो, आप या तो एक कॉन्ट्रावेरिएंट मेट्रिक टेंसर ले सकते हो। अभी आपको समझना होगा कि आपको कन्वर्ट किससे किसको करना है। जैसे कि मेरे पास कोवेरिएंट है, मेरे को कॉन्ट्रावेरिएंट चाहिए, तो कोवेरिएंट मतलब इंडेक्स नीचे, कॉन्ट्रावेरिएंट मतलब इंडेक्स ऊपर, तो नीचे से ऊपर लाना होगा, तो ये इंडेक्स को मैंने हटाना होगा ना, तो उसके लिए मैंने क्या किया, याद रखना, कोवेरिएंट इंडेक्स को अगर कॉन्ट्रावेरिएंट में कन्वर्ट करना है तो मुझे कॉन्ट्रावेरिएंट मेट्रिक टेंसर से मल्टीप्लाई करना होगा। कॉमन इंडेक्सेस को हटा दो तो ये आप लोगों का ए म्यू बन गया। इन अ सिमिलर मैनर मान लो मैंने मेट्रिक टेंसर को कुछ ऐसा लिखा, तो दिस इज अ कोवेरिएंट मेट्रिक टेंसर, मैंने मल्टीप्लाई किया उसको ए न्यू से। अब जरा फॉलो करना है, यहाँ पे मैंने क्या किया, दिस ए न्यू, दिस इज अ कॉन्ट्रावेरिएंट टेंसर, उसको मैंने एक कोवेरिएंट मेट्रिक टेंसर से मल्टीप्लाई किया, तो ये आपका बन जाएगा एक कोवेरिएंट। मतलब समझ में आ रहा है ना क्या किया मैंने, पहला तो ये कोवेरिएंट था, कोवेरिएंट को कॉन्ट्रावेरिएंट में कन्वर्ट करने के लिए मैंने मेट्रिक टेंसर से मल्टीप्लाई किया, पर उसका इंडेक्स ऊपर है। यहाँ पे क्या किया, यहाँ पे मैंने कॉन्ट्रावेरिएंट को कोवेरिएंट में कन्वर्ट किया, उस पहले में मैंने कोवेरिएंट को कॉन्ट्रा में कन्वर्ट किया था। समझ में आ रहा है ना, आप लोग ये चीज जरा नोटिस जरा एक बार करो, बिकॉज दिस इज व्हाट आई विल बी डूइंग ओवर हियर। ठीक है, जैसे कि देखो यहाँ पे मैं करूंगा क्या, दिस इज अ मेट्रिक टेंसर, the difference is that I in place of writing g mu nu I have written eta mu nu, right? Okay, so what I'll do is, this is a metric tensor जिसका इंडेक्स नीचे है, उसके साथ आपने a mu को मल्टीप्लाई किया जिसका इंडेक्स ऊपर है, तो अगर आपने इस दोनों को मल्टीप्लाई किया ये आपको a mu देगा ना, खुद देख लो यार। एक मेट्रिक टेंसर जिसका इंडेक्स नीचे, उसको मल्टीप्लाई किया एक कॉन्ट्रावेरिएंट के साथ जिसका इंडेक्स ऊपर है, तो मल्टीप्लाई करोगे तो कॉमन इंडेक्सेस हट जाएगा ना, तो यहाँ पे भी वही किया मैंने, नीचे मतलब इस मेट्रिक टेंसर को इससे मल्टीप्लाई किया, दिस बिकम्स a mu। समझ में आ रहा है ना, सो दिस इज हाउ यू राइट द इनर प्रोडक्ट और द डॉट प्रोडक्ट ऑफ टू 4 वेक्टर्स। तो लास्ट में आप लोगों को बस इतना पता चला, अगर इसको मैं तो यू कैन बेसिकली यू कैन टेक अ स्क्रीनशॉट ऑफ इट, डन। ओके, सो basically what you have learned today is, in order to call any quantity a 4 vector, it must obey 2 rules. The first rule is that it must obey a transformation equation, and the equation was x bar mu or x bar mu summation mu goes from 0 to 3 lambda mu nu x mu. This was the transformation rule, very important. And the second was that the inner product and the must be constant. Now the inner product of any 4 vector can be written as a mu equal to minus a naught square plus a1 square plus a2 square and a3 square। बात को सुन के रखना, ये a स्क्वायर का होल स्क्वायर नहीं है, इसको एग्जाम में जाके a to the power 4 मत लिख के आना, दिस इज a2, that means the y component of the y component of the a vector or whatever it may be। तो ये होता है इनर प्रोडक्ट। मेरी बात को समझो, लॉजिकली जरा समझो, 2 वेक्टर का अगर तुमने डॉट प्रोडक्ट लिया या इनर प्रोडक्ट लिया 3 डायमेंशन में, वो आपको ऐसा लिखना होता है। ऑन अ सिमिलर स्केल, ऑन अ सिमिलर नोट, अगर आपने 4 वेक्टर का इनर प्रोडक्ट लिया या डॉट प्रोडक्ट लिया, उसको ऐसा लिखना होता है। सिंपल बात, क्या बोला, 2 वेक्टर है यूक्लिडियन स्पेस में, अगर आपने उन दोनों यूक्लिडियन स्पेस में डिफाइन करने वाले वेक्टर्स का अगर आपने डॉट प्रोडक्ट लिया या इनर प्रोडक्ट लिया, वो ऐसा होगा। ऑन अ सिमिलर नोट, अगर आपने किसी भी 4 वेक्टर्स का इनर प्रोडक्ट लिया, दैट वुड बिकम समवॉट लाइक दिस। ओके, फाइन। सो थैंक यू फॉर टुडे, विल बी कंटिन्यूइंग इन द नेक्स्ट लेक्चर। थैंक यू, गुड नाइट।